Hello and thanks for having chosen to watch my talk. My name is Florian Puchhammer from the Basque Center for Applied Mathematics in Bilbao in Spain. And today's talk is based on a joint work with my advisors Elena and David, and with three of my predecessors, Julian, Tiana, and Wayne. And today's problem is an inverse problem in geology which we want to solve by Hamiltonian Monte Carlo. The problem itself is called the 1D Magnetotelluric problem, and it basically considers a very simple type of media, so we just have one-dimensional layers stacked on each other, and each layer is characterized by a base depth, L, and electromagnetic resistivity, ρ. And the top layer is usually just air or water. The way it works is the following. So we have some changes, some fluctuations in the Earth's electromagnetic fields, which are caused by natural sources such as lightnings or something that has to do with the sun and stuff like that. And we measure these changes by a receiver, which we place just a little bit under the Earth, a few centimeters. And we measure these changes in form of the impedance, C, at certain frequencies, omega k. And the impedance carries some information about, so it varies with respect to the resistivities and also the geometry of the problem. And the good thing about the magnetotelluric method is that it's completely non-invasive, so we don't need to drill holes or anything. We just really rely on completely natural sources. The forward problem looks as follows. So we're given the resistivities, the geometry of the problem, and the frequencies, and what we want to compute are the impedances. And these are governed, basically, the dynamics are governed by Maxwell's equations, and the problem is very well understood, and we have a very efficient forward solver. The inverse problem is, as usual, more sophisticated, but at the same time more realistic. So it's basically what we want to do. We have some measurements of the impedance obtained at certain frequencies, and we know the geometry, and what we want to infer are the resistivities, ρ. Since I already used the term infer, the solution approach is Bayesian inference, so we choose the posterior proportional to the likelihood times a prior, and we sample from this posterior with three different samplers, namely Metropolis Random Walk, HMC, which was introduced by Duane and others in '87, but was translated into computational statistical setting by Neil, and modified Hamiltonian Monte Carlo, which was just very recently translated into the statistical setting by in this paper under the name Mix and Match Hamiltonian Monte Carlo. And the goal of today's talk is, first of all, that we can basically forget about Metropolis Random Walk. These two guys perform much more efficiently. And then again, that the modified methods perform much better in terms of efficiency than the Hamiltonian Monte Carlo method itself. Just some preliminary remarks. So usually the geometry is also part of the problem. So there are a huge deal of papers dealing with that under different assumptions and what is better and so on and so forth. So for now, it just shows to be a temporary simplification that we consider the geometry given, but we want, at the end of the day, we need to do that too, of course. In this inverse problem, the solutions may not be unique and sometimes they aren't, so a probabilistic approach is probably a wise idea. We don't have to just consider the one-dimensional problem. We can also go to higher dimensions. But let me just say that it gets computationally demanding very quickly because the problem has a much higher dimensionality, high covariances between pixels or voxels, and the forward solver is also much less efficient. But there are people who have dealt with that, so there's also some literature on that here. There has also been a recent work that investigated this problem in combination with HMC by Conway and others. And they compared two samplers, the no U-turn sampler with the empty dream sampler, and they also commented a little bit on the efficiency. But the problem usually is if you have two such black box algorithms, it's really hard to talk about efficiency in terms of quantitative data. And also what they did not include was modified Hamiltonian Monte Carlo methods, and this is what this is one of the big selling points here. The plan for today is that first of all we derive the model description in terms of Bayesian. We quickly discuss the different samples we're going to use, and then I show to you something that is very sampler specific in terms of Hamiltonian Monte Carlo and MHMC, namely choosing integrators, and I'll present to you two adaptive methods, the SAIA and the SAIA, which were also developed in the course of this project. And then we'll test our things at a benchmark problem. Okay, so for the model description, so the goal that we want to do is we want to infer the log resistivities, so the log of the rho chase, which I denote by theta, and we want to do that on the basis of certain measurements at certain frequencies. How we're going to do that, I already mentioned that, the Bayesian formulation, and we choose a sampler, draw some samples from this posterior, and then we just use a Monte Carlo algorithm to estimate some expectation. So this is nothing new. How do we choose the likelihood? So basically we just consider additive noise. So the measurement is the true impedance plus some noise term, which are independent with respect to k. So epsilon 1 is independent of epsilon 2 and so on and so forth. And then the prior can be rewritten very compactly in this form. The only thing we have to be a little bit more careful about is that the impedance is actually a complex number, so we have to adapt the noise accordingly. And this is done by just considering it as real part plus imaginary part. The real part is a certain normal vector. The imaginary part is a certain normal vector. The two are independent, and voila, the likelihood is finished. For the prior, we chose one that considered only bounded resistivities, so the rho J is always between this, within this bounds and within these limits, and we also assumed that the layers are independent. Okay, and then we choose the prior such that the log resistivities are uniformly distributed within corresponding bounds. The big advantage of choosing such a prior are that we can scale up to large orders, but at the same time the posterior will not get too wide, and it's easy to handle because we only require very little information. Okay, requiring little information has basically two sides, so it's also a big disadvantage because we have to make some, for instance, unrealistic assumptions, because at some points independent layers will not, there's sometimes the case, but not always. And we also have the suspicion that it mixes badly, the boundedness mixes badly with HMC algorithms. So probably in the near future we try some unimodal densities with some hyperparameters, but for the time being we just leave it at this simple setting. And just a small technicality, so we wanted to use log resistivities, but we've formulated everything with respect to resistivities. So we just use a variable transformation, and this, after this transformation, this is what the final posterior looks like. Okay, now to the samples. As I already told you, we use three different acceptance rejection sampler: Metropolis Random Walk, Hamiltonian Monte Carlo, and Modified Hamiltonian Monte Carlo. I don't think I need to point out to you what random walk actually is, only that sometimes it takes a long time to explore the state space. So, and this is a big downside in terms of efficiency. One thing how you can improve on that is Hamiltonian Monte Carlo, which was originally developed for molecular dynamics, and the trick is to mimic somehow particles in a Hamiltonian system. So we have a position variable and a momentum variable, and we consider the energy given by the Hamiltonian consisting of the sum of the potential energy with the kinetic energy. Here M is some mass matrix. And now in the statistical setting, we just augment the distribution by a momentum variable. So we draw, at each iteration, we draw this momentum variable, augment the distribution in the following way. This is just a definition again, and here we see how we do it in a problem outside of molecular dynamics. So we take the potential energy as minus the log of the posterior. And the way we propose new states now is by solving Hamilton's equation. So this is just a system of partial differential equations. And this is the way we choose new states. And now we can use the conservation of energy, remember the energy is given by the Hamiltonian, to see that the acceptance probability, which is nothing but this here, so Hamiltonian at new state minus Hamiltonian at initial state, which are equal. So this is equal to 1 now. And after that, we just discard the momentum and keep theta, and that's how it works. So we've just seen in theory, by the conservation of energy, the acceptance rate is 100%. In reality, we have to be a little bit more humble because actually we rarely can solve Hamilton's equations exactly. And this is where numerical integrators come into play, which we denote here by capital psi, and delta t is the step size, and L is the number of steps we use for this integrator. Now we can get acceptance rates smaller than 100%, but it's only because we make some numerical errors when we use an approximative scheme. And of course, the selection of delta t and L is very important for the problem at hand, but it's really not obvious. So for instance, we want to generate proposals far away from the previous one, so we fix some final integration time t, which is given for in terms of delta t and L as the product. And in terms of efficiency, so for instance, if we want to have more accurate results, we will usually just take delta t smaller, but at the same time, to maintain this t, we have to use a huge amount of steps, so acceptance rate increases, but efficiency decreases. So we have to make a certain trade-off here. Okay, and the pros and cons very quickly summed up are that with Hamiltonian Monte Carlo, it's possible to accept distant proposals very frequently, and this makes space exploration much more efficient. Basically, this is the same. This points out the same. And remember the mass matrix we had in the previous slide. So where am I? This guy here, or here. In molecular dynamics, it's determined by the system, but here we can use it as a preconditioner. On the cons side, we have, of course, we have some computational overheads because for Hamilton's equations, we need gradients. And we have a delicate tuning problem. So we need to choose an integrator, we need to choose the step size, and we need to choose the number of steps. So I just put the HMC algorithm here in case somebody wants to pause and have a look at it, but I will not go through it right now. Basically everything is explained. But I'll explain to you the modified Hamiltonian Monte Carlo algorithm. So once again, let me point out that for the statistical setting, it's been translated just very recently in this paper. And MHMC comes with two important enhancements. First of all, it performs importance sampling. And secondly, it uses a partial momental update. And I will explain these two features now. So first of all, importance sampling. What we do is we replace the true Hamiltonian by a different one. So the true density by a modified density with two objectives. So first of all, the new Hamiltonian should be preserved better by the integrators we use to give a higher acceptance rate. And at the same time, the new Hamiltonian should be close to the old one so that the importance sampling weights have low variability. And a good choice is, I just put the word out there, it's a truncated modified Hamiltonian of order 4 based on a two-stage splitting integrator. Well, as we wished, with this choice we get the high acceptance rate because it's well preserved under this kind of integrators. And we also incorporate second order information of the target distribution, which again can be just extracted from simulation data. So the overhead is the additional information required is limited. But of course, we have some computational overhead, so we have to be very considerate about this when we talk about efficiency later. The second improvement is partial momentum update. And the problem with HMC is that at each step we just throw away the momentum at each iteration step. And in doing so, we might lose track of a good search direction. So what we could do is we just take the old momentum from the previous step, draw another random number, and just take as new proposal for the momentum a linear combination of the old momentum and this random number, which is parameterized by this number phi here. Then we perform a metropolis test. Unfortunately, this is necessary after importance sampling. And after this momentum metropolis test, we have a new momentum P, or an old one. Then we just proceed as usual. So we generate proposal from Hamilton's equations and so on and so forth. And at the very end, we have at the very final metropolis test, we have a slight difference. Namely, if we reject the proposal, we flip the momentum. This has the following reason. First of all, what it helps the whole thing, the PMU, is we can keep track of good directions, but if it's rejected, we can dispose of a bad one very quickly. We just go in the opposite direction, and at the same time, still the detailed balance condition is fulfilled. The downside is we have another parameter to tune. Okay, here's the complete algorithm. So if you want to look at it, just pause. I'll go one slide further, or maybe two. Okay, splitting integrators. So now we know why integrators are important, but we don't know how to construct them or which ones to use. So one way to do it is to split the system up into things that act on delta only, theta only, and things that act on P only, so-called drifts and kicks. And they have exact solution flows. So this would be a drift that only acts on theta, and this would be the kick, which only acts on P, the momentum. And one integration step of time delta t can now be defined as a palindromic sequence of drifts and kicks, which have varying time steps. So the time steps for the kicks are parameterized by this b, and it's always delta t over 2 by for the drifts. And for the final integrator, we just take the L-fold concatenation of these single steps. A popular choice is usually taking b equal to 1 on 4, because this is just two consecutive steps of the velocity relay algorithm, which is more or less a standard choice. Yeah. Okay, so now how can we tune our integrators? So basically tuning just means fixing b. And each b defines a different integrator, and each such integrator has a different stability region. The largest one is for the two-stage velocity relay. We also want to choose b such that some notion of error becomes small, of course, but at the same time, we want to be able to pick a delta t that is stable, still large enough such that our algorithm is efficient. And of course, this whole thing should be somehow problem specific. The idea is to do the following. So we adapt b to the time step such that we have the same stability limit as the largest one obtained by the two-stage velocity relay. And we want to minimize the bound on the expected energy error from the harmonic oscillator. And to make it problem specific, it should carry some system specific information, which we can get during burn-in. One way to achieve that is summarized in the SAIA algorithm, so statistical adaptive integration approach, which basically relies on non-dimensionalizing the time step in the first place. So we go from delta t to h. And in molecular dynamics, which is basically which is referred to also as the SAIA algorithm there, we're given the angular frequencies of two body interactions, and for h, we just take a safety factor times the maximum frequency times delta t. And in doing so, we get a canonical stability interval from 0 to 4. Now, how can we do that for SAIA? So what are omega 1 up to omega d? We don't know. We can try something very similar. So we just say h is a safety factor or scaling factor times something relying on the frequencies times the time step. And we assume that the distribution can be approximated by a Gaussian. So this is somehow the equivalent of a harmonic oscillator. Okay, now the omega j's make sense as the eigenvalues of the Hessian of the potential energy, which we can estimate during burn-in. Given the frequencies, we can also easily estimate S with burn-in data. However, this first step already might be quite expensive, so what we also did is we developed a routine to estimate this product directly from burn-in data. And finally, for the minimization step of the expected energy error, I put two references here. The first one here that derive a certain integrator, and this is basically the development of the SAIA algorithm. And this is what it looks like in the end. So in the x-axis we have the time step. At the y-axis we have the integrator parameter b, and we see that basically it just gets adapted with respect to time, and at the end, at a certain point, it just is the same as the two-stage velocity relay to keep the stability limit, interval maximal. Okay, for MHMC, we can derive SAIA, and it works basically exactly the same as for HMC. The only thing is that here we have to use this different Hamiltonian, so the truncated modified Hamiltonian instead of the true Hamiltonian, and basically then everything works out just the same. There's also, for the detailed analysis for minimizing the expected energy error, I put two papers here where this is done. It is called the Maya algorithm. And as a small side perk within the paper where this Maya is developed, there's also a routine to tune this PMU parameter, and we can do something very similar to that one. And the gist of this routine is that we aim at a specific momentum, a targeted momentum acceptance rate, and a default value, a reasonable one, would be 95%. Okay, now as to our benchmark, let me very quickly sum up which metrics we're going to use. So we will take a look at the acceptance rate, of course. We will consider the minimum effective sample size, which means basically the number of uncorrelated samples. We normalize this one with respect to time to get the effective sample size, so to say. We take a look at the Monte Carlo standard error and the worst case scenario, so the maximal one. To get an efficiency metric, we just take the inverse, so that bigger is good again, and normalize it with respect to computation time. And to look at accuracy, we consider the potential scale reduction factor, which basically takes care of how well we searched our parameter space. And the dist is just the relative distance between the impedance of what we measured and the impedance of what we estimated. And for all experiments, we use our own software developed at Puchhammer, which is called HICS, Hamiltonians in Computational Statistics. And to get a very clear idea about this metrics, we repeated each experiment 50 times. Yeah, 50 times. Okay, and this is what a benchmark problem looks like. So we have 5 layers. It's quite low dimensional still. We measure at 14 different frequencies, and we choose them such that the logarithms are evenly spaced. And for our initial measurements, we just put the entire setting into the forward solver and perturb the result by 2% noise. And this is what the benchmark problem now looks like. So here the top layer, we have air, then we have a very thin resistive layer, then we have a thin conductive layer followed by a mediocrely thick resistive layer, and then we have 2 very conductive layers, which are very huge. The parameter selection, so just to make everything short, for each sampler, we tried a couple of things and chose the best parameter setting. So this is what we get for the random walk. For the HMC parameters, we tried a lot of things too, but basically at the end we found that our proposed default setting is actually the best. So the default setting meaning that we take the SAIA algorithm and evaluate it at half stability limit, and the number of steps should be proportional to the number of steps times the step size, so the integration time should be proportional to the dimension. For MMHMC, it's quite similar. Again, integration time should be proportional to dimension, but it's a little bit lower for this one. We take the SAIA algorithm at half stability limit, and as a targeted momentum acceptance rate, it's 95%. Okay, here we put a lot of justification of why this of what we've tried, so that this is really the best, but it's also what we suggest to use as default values. Okay, now my screen froze. Okay, we're back on track again. Okay, so let's quickly go into accuracy of our sampling method. So here I computed for each layer a kernel density estimate, and on the y-axis here we have the depth, and here we have the log resistivities, of course. And we see that actually we are quite certain about our estimates, except for this layer here, but that's something that's also somehow recorded in literature, that if we have a resistive layer that follows a conductive layer, this is usually a hard thing to do, and we shouldn't worry too much about it. On the right-hand side here, I put the impedance values in the logarithmic scale as a function of the frequencies at which we measure. The big dots are the impedance values that we measured. So that's input values basically, and the small dots are what we get from our from our sampling. Blue and red for the real part, green and yellow for the imaginary part, and we see actually that in terms of impedance we're even more sure about what we sample here. Now let's go to the efficiency. So having chosen the best parameter setting for each method, we now draw up this table, and we see basically that, taking a quick look, random walk is just off the charts in a negative way. So no chance to compete with HMC or MHMC. Now when we compare HMC and MHMC, we see that actually in every efficiency metric, high is good, remember, we're doing way better with MHMC than HMC does, and the improvements are around 30 up to 35–40%. And here I put some pictures about the direct comparison of HMC with MMHMC. In the top line, we see a comparison of, we see the ratio of efficiency matrix. In the numerator, we put the MHMC, the modified HMC metric. In the denominator, we put the HMC metric. And in the lower half, we just plot the absolute efficiency metrics for each method. The first picture takes care of the acceptance rate. The second one is for the effective sample size. And the third one is for the Monte Carlo standard error, the efficiency version, so high is better, high is good again. On the x-axis, I put the non-dimensionalized time step that we got for MHMC, and here as a reference value, this is the half stability limit which we get for HMC with the SAIA algorithm. And what we see entirely from these pictures is basically that no matter if we underestimate our MHMC results a little bit, we always do better than HMC, and the thing we lose to our standard setting that we have to choose the half stability limit in absolute numbers is actually really good. So even if we vary a little bit, we still get very stable results with MHMC, still also with HMC, but it deteriorates much more quickly than with MHMC. So just very quickly, the gist is of this, especially of this lower line, is that the gist of all this is that our default setting that we proposed, so stability, taking half stability limit, is actually a good setting. So let me jump to the conclusions. So what did we do today? So we introduced the one-dimensional inverse magnetotelluric problem and derived a Bayesian formulation for it. And we also put it in the context of Hamiltonian Monte Carlo. So I explained HMC, not so much GHMC, I forgot to remove that, sorry, and modified Hamiltonian Monte Carlo samplers, and we identified that we actually have a really delicate tuning problem. But the first thing to tune is the integrator, and I presented some adaptive choices for doing that for HMC and MHMC, called SAIA and SMAIA, as an alternative to the standard choice, which would be the velocity relay. And for the other parameter, I presented a very reasonable default setting. In a numerical study, so one benchmark actually, we compared random walk with HMC and MHMC. So random walk did not perform too well as expected, and when we compared HMC and MHMC, we saw that the modified version just, in terms of efficiency, just outperforms HMC significantly by 30 to 40%, and that our default parameter setting is actually quite successful. And some imminent things we need to study is, first of all, to try more sophisticated priors, especially unconstrained ones, to keep the geometry in the set of unknowns. And thirdly, maybe we need to try our method in combination with field data. Okay, so that's it for my talk. If you have any questions or remarks or want to talk about stuff, just reach out to me. So my email address is on the first slide here. Thanks again for choosing my talk, and I hope you enjoyed it.